Well, that didn't work properly, did it? Cool. You see me all right? Everything okay? Everything looking good there? Yes? Well, regardless, here I am. Just give me a thumbs up in chat or something. Just let me know that everything's coming through. Wee. Good, good, good. Okay, so obviously there's a, as always, a little bit of delay between me saying stuff and you guys actually hearing it. I apologize as well for the darkness of my face here. It's still light outside, and you know how cameras work, right? They don't have the dynamic range to display excuse me, all the colors. Right, so here we are. It is now 20 past 6. Should we go over a few things? I suggested that we go over a quick recap of systems architecture if you want it. Although I think my video on systems architecture is fairly extensive, so I might not need that. Maybe we'll just go over the registers themselves and maybe cache and stuff like that. But I think the real meat and potatoes of this whole thing is going to be binary conversions, converting from Daenery to binary, from binary to Daenery, from Daenery to hexadecimal, from hexadecimal to Daenery, from binary to hexadecimal, from hexadecimal to binary, binary addition, binary shifts, character sets and how they work, storing images, how that works, storing sound, how that works, and calculating file sizes thereof. Do you have any preferences to what should be covered first or not? No preference. Right, okay, I'll tell you what then. So if I'm just gonna, I will copy that and I'm gonna paste it in here, which I am going to, let's just make that cha-ching. There we go. So I got my little text thing here. So systems architecture recap. I'll put each of these on a new line as well. Binary conversions, what else we got? File size, calculations, storing images. Maybe I should separate these things. Storing images, sound and text as binary. Don't know what that is. Binary. Okay, so systems architecture recap. I've been over this multiple times, but this still seems to be an area that flummoxes people. So we're not going to do any volunteering or anything like that. And right. First of all, when I first taught you guys this stuff, this was the model of the CPU that I used. Obviously, the inside of the CPU doesn't actually look like this. You do not need to be able to draw this diagram. You don't need to understand what any of these commands, these instructions actually do. You don't need to know any of that stuff. The things that you need to know is what happens during the fetch, decode, execute cycle, and you need to know how instructions are fetched from RAM, how they are decoded, how they are executed, and you need to know the names of these registers. Okay? So, PC stands for program counter. If you don't already have it in your notes, you should make a note that the program counter stores the address of the next instruction to be fetched. So whatever number is in the PC, that is the memory location that we're going to go to in order to fetch the next instruction. Okay, so if the value in this example here, if the value in the PC is 3, I know that the next instruction to be fetched will be STA013, for example, right? It starts at 0. It generally goes up each cycle, but just because it goes up each cycle, it doesn't mean that that's necessarily the position in the program, because you can jump around, but you don't need to know that stuff. Let's just stay focused on what you do need to know. PC, program counter. Okay. The MAR is the memory address register. This holds the address in memory that we are about to either fetch something from or put something in. Okay, so all of the things that are stored in memory have to have an address. The actual memory addresses are not written in Daenery like this. They are obviously binary addresses, or they're more commonly viewed as hexadecimal by programmers. But this just makes it easier to see. So if we are going to be fetching the instruction at memory location 3, that address, number 3, needs to go in the MAR, so that when the CU says, oi, read that memory, it can then look up that address. The MDR is the memory data register, and that stores the values that have just been fetched from memory, or the values that are about to be stored in memory. Okay, so during the fetch process, once we've copied the value from the PC into the MAR and we've fetched the instruction from the memory store, that instruction will be stored in the MDR when it's first copied across. It then gets copied into the CIR, the current instruction register, but the only 2 registers that are connected to RAM in any way are the memory address register, the MAR, and the memory data register, the MDR. Okay. The MDR also, if we were storing some value from the accumulator in RAM, the MDR, we would copy the value from the accumulator into the MDR. We would copy an address into the MAR, and then when we push the data across the data bus into memory, it's stored at that address. You don't need to know the ins and outs of that. Okay, I'm just giving you a basic rundown of these components because I don't want to spend an awful lot of time going over systems architecture again when I already have a pretty comprehensive video on it. Okay. So PC, program counter, MAR, memory address register, MDR, memory data register, CIR is the current instruction register, which stores the instruction which is currently being carried out. The accumulator is also a register, sometimes abbreviated ACC. Okay, accumulator, and that stores the results of any maths that are any math values that are currently being calculated, store in the accumulator. These other letters here, these are 2 I guess sections of the CPU that you need to be aware of. 2 components of the CPU is probably a better way of saying it. The CU is the control unit. It is the CU that controls each stage of the fetch, decode, execute cycle. It is also the control unit that says whether we are going to read from memory or whether we are going to write to memory. Okay, so the control unit is the thing that controls the whole process. The ALU is the arithmetic logic unit. That's where all of the maths are carried out. That's where all of the logical decisions like and, or, and not comparisons are made. This is the thing where almost all of the instructions are probably going to be executed. They're going to be carried out by the ALU, unless they are a load or store operation. Okay, so any maths is carried out here. Think arithmetic, maths. That's what it is. Okay, so in terms of what you actually need to know for the GCSE in the fetch, decode, execute cycle, you need to know that the PC stores or holds the address of the next instruction to be fetched. That address is looked up. So the PC is copied into the MAR. You don't need to know the specifics of that, but that address is looked up in memory, and the instruction that is stored at that address is fetched and stored in the MDR. It's copied into the CIR. the CIR will decode that instruction into an opcode and an operand. The opcode is the actual instruction itself, what it is that you need to do, and the operand is the data that you are doing it with. And then finally, the instruction is executed. So the opcode is executed using the operand data. All of that process is discussed in extreme detail in my other video about systems architecture, so I'm not going to recap that now. I just wanted to have a bit of a do-over here, right? Just to make sure that you guys understand all of that. So I don't know how many of you there are currently watching. According to my little stats thing, there's four people. Wicked. Hey, you know, as long as you guys are getting something out of it. Are you guys happy with the components in the CPU? Is that it? Is that good? We may never know. We may never know. But regardless, I'm going to move on now to look at cache, clock speed, and number of cores and how they affect the performance of the computer. Okay, so I have to go for some squares. Squares? Okay, yeah, cool. That's fine. You do whatever that means. You do that. This will still be available if and when you get back. Right, so cache, clock speed, number of cores. Let's just quickly go over what they mean and why they can improve. Can I have my children back? I don't have your children. Don't know what's happened to them. Maybe if you write a strongly worded email to the police, they might be able to bring them back. Okay, so first of all, we're not going to do that. We're going to talk about cache. Cache is a form of memory. Yeah, the cache is actually located on the CPU. So it's part of the CPU. The main memory store is not part of the CPU, that is your RAM. Okay, now if you think about it in those terms, it should be fairly obvious that cache is, if you like, closer to the CPU because it's actually there. You don't have to send data down buses in order to fetch the data from RAM. You don't have to wait as long for the RAM to search for the stuff that you're looking for and then bring it back. If you're accessing something in the cache, it is way, way faster for the CPU to access the cache. Okay. In addition, cache usually uses a special type of memory called static RAM, which in itself is a lot faster to access than the dynamic RAM, but there's advantages and disadvantages. However, cache is expensive. Because cache is expensive, we tend not to have too much of it. Okay, the analogy that I use is this, right? Imagine that you have a book chained to the wall on the opposite side of the room. That book is filled with information, okay? And you're given a list of information that you have to look up, okay? You're only allowed to look up one piece of information each time before you go back to your seat and then write down what it is that you've just found, okay? So you can only remember that one fact. You're only allowed to actually do anything with that fact when you get back to your seat. It's obviously going to take you a long time. If you've got 100 things to look up, you've got to get up out of your chair, you've got to walk across to the opposite side of the room, grab the book which is chained to the wall, look up the thing that you have been tasked to look up, grab that bit of information, remember it, come all the way back to your chair and then do something with it. And then, if you're asked to look up the same piece of information again, you have to get up again and go all the way over to the other side of the room again before you can go back and do anything with that information. It's obviously very slow. Okay? You're getting up, you're going across. This is equivalent to a CPU that does not have any cache. It's going to the main memory store every time. If you imagine that book chained to the wall is like the main memory store. That's your RAM. and you're getting up and you're going and fetching an individual item from RAM every time. It's slow, okay? I mean, it's slow in relative terms. To us as human beings, it's blindingly fast, but to the CPU, it's pretty slow, okay? So for the example that I've got here, how many legs does an ant have? You have to get up, go across, look up the information in the book. Oh, an ant has 6 legs. Cool. Let's go all the way back. Cool. Right, what's the next question? What color is an anteater? All right, let's go to the book. Let's look up that information. An anteater is grey, and sometimes they have a black stripe down them. Cool. Okay, we found that information. Let's go back. How many ants can an anteater eat in one day? So all the way we go back to... find out how many ants an anteater can eat in one day. I don't know. I'm going to guess 100,000. Let's say 100,000 ants eaten in one day. And it comes all the way back. So then the next question is, what is the total number of ant legs which the anteater consumes, right? Well, in order to do that, we have to go back to the book to find out how many legs an ant has. Then we have to go back to the book to find out the total number of ants that they can eat. And then, and only then, we can do the calculation. We're going to have to go backwards and forwards, 5 or 6 times in order to get that information, right? But imagine, instead of that big book chained to a wall, you have a post-it note. You can make a note of the information that you've just fetched on that post-it note, right? So you go across to the big book, yeah? You find out how many legs an ant has, and you can just write that down on your post-it note, so that if you're asked that question again, you don't have to get up and go all the way over to the book. You can just look it up on your post-it note, right? So again, here, how many legs does an ant have? Let's go and fetch that information. We come back, we write down an ant has 6 legs on our post-it note in front of it. What color is an anteater? We go and find that information. We write down an anteater is grey with a black stripe. How many ants can an anteater eat in one day? We get up and we go and we find out how many ants an anteater can eat in one day, and it's 100,000. What is the total? That's a mistake there. What is the total number of ant legs which the anteater consumes? Well, cool. I've already written down how many legs an ant has, and I've written down how many ants an anteater eats in one day, so I can do that calculation without then having to get up and make the journey again, right? So we only need to go to the book on the wall 3 times because we've written down that stuff on our post-it note in front of us. Yeah, so I know that analogy seems a little bit strange, but it's a good way of thinking about it like this. If you imagine you have that book chained to the wall and that's your memory store and it's slow to get up and go and get it, if you have that post-it note, it speeds things up. Cache memory is like the computer's post-it note. Yeah, it's a very small but very fast area of storage on the CPU, literally on the CPU, where frequently and recently accessed data is stored. Which means that if that data is requested again, computer doesn't have to go and look it up again. It's right there in front of it. Yeah. So in answer to the question, how does cache affect the performance of the CPU? The more cache you have, the more of those little bits of information you can store directly on the CPU. And the more of those little bits of information you can store directly on the CPU, the less you will have to go to main memory. Therefore, having more cache on your CPU will speed up the computer because it does not have to access the main memory store as frequently. Okay, you don't need to know about that. So these are the key points. The more cache we have, the more fast access to memory we can use. The more cache we have, the faster the CPU can carry out instructions. Yeah. So obviously the cache is not big enough to move all of the system memory to the cache, and also having too much cache can actually slow things down. Because if you think about it, if you've got one post-it note, well, it's easy to scan through the information on that one post-it note. If you've got a whole book full of post-it notes, it's going to take time to look through that stuff. Sometimes it's just going to be quicker to go to the big book where it's easier to look the stuff up. Okay, so to put it simply, the more cache available, the faster the CPU, because it does not have to fetch frequently and recently used pieces of data from the main memory store every time. Does that make sense? Give me a thumbs up if you exist, or nothing if you don't exist. According to this, we have four people watching. So well done, you four. You're keeping the flame alive. At least I know that maybe 4 people will do well in their exam on Monday. We shall see. 5 now. 5. Someone's proven me wrong. We got 5 viewers. Thank you, Bright23, for your 5 thumbs up, whoever you may be. So that's cache. Okay. There's 2 other forms of measurement in terms of the performance of the CPU. If you are still there, what are the other ways to measure the performance of a CPU? We've got cache. There's 2 other main ways that we can compare and measure the performance of a CPU. Oh no. No one knows. Amount of cores. Yes, that's one way. And the other way? Clock speed. Excellent. You guys are knowledgeable, let's say. Right, so let's have a look. We don't want volunteers. I can't do this. Right, let's talk about clock speed. Clock speed, on a very basic level, this is kind of like a white lie. It's how many instructions can be carried out each second. If you do A-level A-level computer science, you will understand why that is not strictly true. But in terms of GCSE, that's all you need to know. Okay. Technically, the clock speed is how many fetch, decode, execute cycles can happen in a second. Right? It's measured in hertz. 1 hertz means 1 time per second. 1 kilohertz means 1,000 times a second. A megahertz means 1,000,000 times a second. A gigahertz means 1,000,000,000 times a second. Most CPUs these days are measured in gigahertz. And they range from about 1.6 gigahertz to about 5 gigahertz. I don't think there's anything faster than 5, or if there is, it's not much faster than 5 because that's pushing some theoretical limits. But if you think about it, even a 2 gigahertz CPU, that's 2 billion cycles per second. In theory, that's 2 billion instructions per second. That's really fast. Yeah, that's really fast. When you compare it to like computers in the 1990s that were operating at, say, 66 megahertz. I mean, 66 million instructions per second is still pretty fast, but it's absolutely nothing compared with 2 billion. Yeah, it's fantastically the speeds have increased so rapidly. Okay, so it stands to reason, right? If you can do more cycles per second, that means you can execute more instructions per second, and that means your programs will run faster, right? One thing to be aware of. When you're asked a question about comparing CPUs, please make sure that you say clock speed and you don't say hertz, right? Compare the hertz. No, you'll get 0 marks. Compare the clock speed. Yes. Okay. So the simple explanation for clock speed: the higher the clock speed, the faster the system, because it can carry out more instructions per second. Okay, there's your 2-mark answer. How does clock speed affect CPU performance? If you have a higher clock speed, your system will run faster. 1 mark. Because it can carry out more instructions per second. 2 marks. Okay. So let's talk then about the number of cores. You'd be hard pushed to find a single core CPU for a desktop computer these days. In fact, even CPUs for mobile devices, tablets, etc., they are multi-core these days. Okay. The thing that you need to understand about cores is each core is effectively its own mini CPU. If I just skip back to my little diagram here, right? This each core inside your CPU will have its own set of registers, will have its own ALU, will have its own CU. So this is obviously a representation of a single core CPU, but if I had a dual core CPU, that means 2 cores, I would have one of these, I would have another one of these. Yeah, and each core can carry out its own fetch, decode, execute cycle at the same time, right? Simultaneously. And that at the same time is an absolutely key point. Okay, so remember, the core of the CPU is where the fetch, decode, execute cycle actually happens. The core has its own set of registers, it has its own CU, it has its own ALU, it even has its own independent cache. Okay, but just because you've got a single core CPU, let's say we've got a single core CPU operating at 1 gigahertz, you've got a dual core CPU where each core is operating at 1 gigahertz. The dual core CPU is not necessarily going to be twice as fast as the single core CPU because they share a memory bus. Okay, so that means that although they can be executing their own instructions simultaneously, i.e. they can run 2 separate programs at the same time, each of those programs, you can only have one of them accessing the memory at any given time. Okay, so I've got a little diagram of it, or a photograph even, in a minute, but the fact that the multiple cores on a single CPU still share the same memory interface means that things slow down a little bit because they can't independently access the memory. Okay, you might have heard about threading though. If you have a program which is threaded or multi-threaded, you might have heard, or has multiple thread support, each individual thread can be run on a separate core, which means that you can sort of like halve the workload and potentially speed things up. Okay, there's a lot of trickiness in that which you don't need to know at GCSE level. So it's an interesting topic, but I wouldn't worry about it at the moment. Okay, the example that I use here, if you imagine doing the dishes, right? If you do the dishes yourself and then you wash them up, it can take a long time. Wash a dish, put it on the pile, wash a dish, put it on the pile, wash all the dishes and then go and dry all the dishes. You know, that's going to take quite a long time. But if you have a friend or a sibling helping you out, one of you can be washing the dishes while the other one dries the dishes. Yeah, you wash a dish, you put it on the pile, and while you are washing the next dish, your friend is there drying that dish, right? So in theory, you can get it done in half the time. Okay. However, there is a little bit of a bottleneck, because obviously if it takes you longer to wash a particular dish, the dryer can't start drying that until you finish washing it. So it's not necessarily going to halve your time, but it is going to fantastically reduce the amount of time that it takes. Okay, so this here is a picture of the internal workings of a CPU. So inside your CPU, there's all this various different circuitry. You don't have to know what all this stuff looks like, but you will notice there is this bit here, there is this bit here, there is this bit here, and there's this bit here, which all look almost identical to each other. Okay, there's some differences in color, but you can clearly make out these individual structures being in the same place. That's because each one of these is a separate core. Okay, and each core has its own set of registers, has its own CU, it has its own ALU, right? So that's why they all look identical. Down here is the shared cache. This bit here is the memory interface. I think I've labeled these. Here's core 0, core 1, core 2, core 3. This is the level 3 cache, which is shared by all of them. They also have level 1 and level 2 cache. Don't worry too much about that. But here is the memory interface. We have all of these separate cores, but they share the same memory interface, right? You do not need to know what the inside of the CPU looks like. I'm just using this as an example. So you can see the fact that you've got 4 cores doesn't mean that it's going to run 4 times as fast, because there is this memory interface bottleneck. Does that make sense to people? Welcome to those of you that are just joining us. I hope this is enlightening for you. I apologise again for the darkness of my face. It's largely down to the fact that the sun is still out. Maybe if I change the camera there, a little bit better. There you go. You kind of see me now, right? That's a bit better, right? Cool. So, cache, clock speed, number of cores. Those are the nice pillows. There's 2 dinosaur pillows there. One of them I got from, I think, Sainsbury's about 12 years ago. It has been restuffed in that time. And the other one I got from, I want to say, Asda about 6 years ago, or maybe longer ago. But yeah, I don't know who Bill is. I assumed it was you, Alfie. Who knows? Who knows? Right. So we're not gonna. You don't. There's no homework. Don't worry about that. So hopefully you guys are now. I mean, most of you said in the class that cache, clock speed, and number of cores that you were all fine with that. I just wanted to go over it just to make sure. Because I know that oftentimes you find people say, yeah, we know all that, and there's some people that sort of go along with it, and maybe they don't. But so that was your opportunity to see that. So. I've gone over systems architecture briefly. Remember, there is that 30-minute-ish video on systems architecture, which I highly recommend watching if you've still got any questions on that. Should we do some binary conversions? That's a thing that we haven't done in a while. Do you want to do some binary conversions? Yes, sir. Do some binary conversions. All right. So in order to do the binary conversions, I am going to have to switch to my amazing improvised whiteboard here. How about that? Huh? Yeah. How about this? I apologise in advance for I'm drawing with a mouse here, so it's gonna look pretty whack. I'm also just gonna have to move that out of the way a little bit. I think I did this in Scratch. What, binary conversions? Okay. Right. So we'll start off with the most basic, binary to Daenery. Okay. You need to know the magic numbers that go at the top of the rows of binary. If you can't remember them, there's a system for getting them right. If you start on the far right with 1, yeah, and you go to the left, doubling each time, then you will get all of the numbers. So we start off with 1, we then have 2, we then have 4, we then have 8, we then have 16, we then have 32, we have 64, and we have 128. What I should have probably done is drawn some lines in here to separate that. So I'll just quickly do that. There we go. Just so that we can split this up. Oh God, I'm sorry. No, I'm not having that. Right. So we're going to build a binary number. Obviously, when you're writing with a pencil in your hand on a piece of paper, this is going to be way neater than what I've done here. This is absolute crime against everything, so I apologize for that. So let's do a binary number conversion. We're going to convert a binary number to Daenery. That's probably the best starting point. So a binary number is made up of a bunch of ones and zeros. So let's have a 1 0 1 1 0 0 1 1. Right? That's the number that we're going to convert. Yeah. If I just write that down so you can see what it would actually look like without this stupid framework in there. 1 0 1 1 0 0 1 1. You will. It's almost guaranteed you will get a question that says take this binary number and convert it to Daenery. Okay, very, very easy to do. Once you've written the magic numbers above each of the numbers in the binary, all you have to do is, if the number is a 1, write down the number above it. If the number is a 0, skip it. Right? You will end up with a list of numbers. So we've got 128. Okay, there's that one. There's a 0 there, so we're going to skip that. We've got 32. We've got 16. There's a 0 there, so we're going to skip that. There's a 0 there, so we're going to skip that. We've got a 2. And we've got a 1. Okay? All you need to do, once you've written those numbers down, is add them up. Okay? So 8, 9, 10, 16, 18, 19 for that column there. And then we have 2, 5, 6, 7 for that column there. And just 1 for that column there. So 1, 0, 1, 1, 0, 0, 1, 1 is equal to 179 in Daenery. Does that make sense? Give us a thumbs up or some other symbol of understanding. The 4 people that are tuned in here. Tack. Yeah, okay, I'll take that. Right, okay. One thing, a top tip, by the way, one way that you can check to see if you're likely got it right. If a binary number ends with 1, it's odd. If a binary number ends with 0, it's even. Okay, so even numbers always end in a 0 in binary. Odd numbers always end in a 1. Okay, that's one way that you can double check to make sure that at least you've got the last digit correct. All right. Cool. I will just rub this out, or maybe I should move it. Let's move it along a bit. There we go. Let's go there. And let's do. You know what? It's a bit too confusing if I do that. I'm just going to rub it out. So let's do a conversion the other way. We will start off with a Daenery number and we will convert to binary. So I'll tell you what, why not start with that 179? Yeah. We've just done it, so we should get the same binary number. Hopefully you guys can remember the binary number. The way that this works is you still start off with those magic numbers. We've got 128, we've got 64, 32, 16, 8, 4, 2, 1. Okay, maybe I should draw that the little grid in there as well. That looks a little bit neater this time. My skills are improving. There's multiple ways that you can do this. One way is to continually divide by 2. We're not going to do that way. This is what we're going to do instead. We start off with 179. We're starting from the left-hand side, so start from the biggest number, okay? And if that number, so we're looking at 128, if that number is equal to or greater than the number that we are converting, we're going to write a 1 under there, okay? So 179, that is greater than this number, so we're going to write a 1 down there, okay? Now, because we wrote a 1 in this column, we then have to subtract 128 from 179. Okay, so we've got 179 here. If we subtract 128 from that number, we end up with 9 minus 8 is 1, 7 minus 2 is 5, and 1 minus 1 is 0. So we've got 51. Okay, so 51 is less than 64. Right, 51 is less than 64. So we are going to put a 0 down here. Because we put a 0 under that number, we are not going to do anything down here. We're just going to keep on with the 51, right? So 51, 32 is less than 51. So remember, if it's If it's equal to or less than, we are going to put a 1 in there. So we put a 1 in there. And then, as before, we're just going to subtract 32. That's a 2, not a 3. 32 from our number. Now, 1 minus 2 you can't do, so we're going to have to borrow. We've got 11 minus 2 is 9. And then that 4 minus 3 is 1. So we're left with 19. And again, we just keep on moving on. We follow the same pattern. 16 is less than 19, so we're going to put a 1 in there. Okay, then we're going to subtract 16 from 19, and 19 minus 16 is 3. Okay, so 8 is greater than 3, so we're going to put a 0 in there. 4 is greater than 3, so we're going to put a 0 in there. 2 is less than 3, though, so we're going to put a 1 in there. And then I'll just move that along a little bit. We can subtract 2 from our 3, and we end up with 1. Okay, and then 1 is equal to 1, so we're going to put a 1 in there. Subtract that 1, and we end up with 0. You will know you are done when you end up with 0 at the end. You might end up with 0 before you reach the end, in which case all of the other numbers are going to be 0. Okay, but we started off with 179 and we got to 10110011, which is exactly the same binary number that we started with last time when we converted it to the Daenery number 179. Makes sense, right? That one's fairly easy. Does that make sense? I don't know. It makes sense to Bright23. Yes, Bright23. Solid avatar as well. I like that dog. It's a good dog. Solid dog. Dog plus 10 points. Right, let's delete this. Should we do some hexadecimal conversions then? Let's convert some hexadecimal numbers. Now, my top tip that I always give to all of my students, and they always seem to forget, is if you are doing a hexadecimal question, it is a good idea to just write down A equals 10, B equals 11, C equals 12, D equals 13, E equals 14, F equals 15. If you write that down at the side, then you have a quick reference table for those letters. I know it sounds weird, right? But writing that down, it reduces the amount of thinking that you have to do in your head. It reduces the chance that you will make a silly mistake like saying C is equal to 13. Okay, so anytime you're dealing with a hexadecimal question, make sure that you write this little table down. A equals 10, B equals 11, C equals 12, D equals 13, E equals 14, F equals 15. It is a tip that may save your life. Well, or at least save some lost marks. So let's do a conversion from hexadecimal to binary. This, in my mind, is probably the easiest of the conversions. Now, one thing to bear in mind, there's a lot of people that I find seem to think that hexadecimal numbers have to have letters in. They do not, right? You could say the hexadecimal number, I don't know, 49, right? That is still a hexadecimal number. Yeah, it's not 49, it's hexadecimal 49. Okay, we are going to convert the number hexadecimal 49. The first thing that you do is you split those digits apart. So we've got a 4 and we've got a 9. I am going to do 2 examples just so that we can use the letters as well, right? Then all you do is convert those letters to nibbles. Okay, so 4-bit binary. So 4 as a nibble is 0, 1, 0, 0. 9 as a nibble is 1, 0, 0, 1. Okay, once you've converted those, you just join them back together and you end up with, in this case, 0, 1, 0, 0, 1, 0, 0, 1. So 49 in hexadecimal is equal to 0, 1, 0, 0, 1, 0, 0, 1 in binary. Okay, if we're using letters, let's have, I don't know, should we do, let's do E3. E3, the most overrated entertainment expo ever. Same deal applies. You split those digits apart. Okay, now in this instance, we've got an E. We have to know what that is in Daenery before we can do the conversion. So E, looking up in my little table, E is equal to 14. Okay, so now we can convert that 14 to a 4-bit binary number, and we end up with, what have we got? 8, 9, 10, 11, 12, 13, 14. There we go. 1110. And then the 3, we don't need to convert that to anything other than the 4-bit binary, so we end up with 0, 0, 1, 1. And as before, you just join them back together. There's my terrible drawing of an arrow there. 1, 1, 1, 0, 0, 0, 1, 1. Okay? And that's that. That is it. Okay? That's hexadecimal to binary. That makes sense to everyone. Should we do it the other way? Because the other way is just as easy. Give me a thumbs up or something, or some sort of comment. We love Mr. Smith. Yes, who doesn't, right? Actually, there's a lot of people that don't love me. Sad, lonely individuals, you know, that either failed in life or are filled with regret every day. But yes, thanks for dropping in, Scarlett. Right, shall we go over the I miss you, G? Yes, same. Is that Ben? I'm feeling that's Ben. Let's do the binary to hex, yeah? Let's do binary to hex. So if I start off, please do how to code, see if my boyfriend is cheating on me, though. He probably is. He probably is. You know, so I guess ditch that 0 and get with a hero. There's my terrible... Don't listen to my dating advice. I haven't had a girlfriend in 10 years. So let's start off with a binary number. I'll draw a line under that, literally. If I have a binary number, I don't know, 0, 1, 1, 0, 1, 1, 1, 1. There we go. There is my binary number. Okay. Now the way that you convert these, you have to split them into nibbles. Okay. There are 4 bits to a nibble, so you just separate those nibbles. Code Alfie some women. Well, see, most coding these days takes an object-oriented approach, and I don't want to objectify women, so you know, you're going to have to do it the old-fashioned way, I'm afraid. So I now have this number here, 0, 1, 1, 0, and I have this number here, 1, 1, 1, 1. So I convert them to Daenery. Remember, we're still using those same binary magic numbers. We've got 8, 4, 2, 1. So 4 plus 2 is 6. And we've got 8 plus 4 is 12. Plus 3, because 1 and 1 is... let's do it the whole way. 8 plus 4 is 12. Plus 2 is 14. Plus 1 is 15. Okay, so we end up with 6 and 15. But the problem now is that we need 2 digits, not 3. So all we need to do is, if the number is greater than 9, if the number is greater than 9, you just convert that to the equivalent letter. Okay, so 15, we look it up in our little table that we conveniently wrote down. 15 is equivalent to F. Therefore, the number 0110 1111, when converted to hexadecimal, is 6F. Oh no, don't fail. Is there anything I can do to help? I will do everything in my power to help. Drop me an email. I'll see what I can do. So that is, we've done Daenery to binary, we've done binary to Daenery, we've done hexadecimal to binary, we've done binary to hexadecimal. Cool. Well, let me know how I can help and I'll do it. All right. So there is one final conversion that we need to do, and that is we've got to do Daenery to hexadecimal, and we've got to do hexadecimal to Daenery, and these are the horrible ones. No one likes doing these, but I'm going to give you some tips on how to do them in a roundabout, nicer way. Okay. I'm in your class, but I never noticed you. I find that hard to believe. I notice all of my students intensely notice them, especially when they're playing games online. Right. So let's do a hexadecimal thing. Oh, I've deleted my my little hex table, so I'm going to draw it again. We've got A is 10, B is 11, C is 12, D is 13, E is 14, and F is 15. Okay, there's our numbers. Right, now, one thing to remember about hexadecimal is that it is base 16. It's base 16. Daenery is base 10. Binary is base 2. Hexadecimal is base 16. And if we just consider Daenery for a moment, if I have the number 375, right, 375, we have some magic numbers here, right? There is units. There are 5 units. There are 7 tens. And there are 3 hundreds. Yeah? The magic numbers go up by 10. You multiply by 10 each time. 1 times 10 is 10. 10 times 10 is 100. 100 times 10 is 1,000, and so on and so forth. With binary, if we have the number 0, 1, 0, 1, 1, 1, or something like that, this one here represents the 1s, this is the 2s, this is the 4s, this is the 16s, this is the 32s, this is the 64s, and so on and so forth. It doubles each time. All right, multiply by 2. 1 times 2 is 2. 2 times 2 is 4. 4 times 2 is 16. 16 times 2 is 32. 32 times 2 is 64. Okay. Hexadecimal is a base 16 numbering system, right? So if we have a number like, I don't know, 3D, right? This column here will represent the 1s. This column here will represent the 16s. If we had another column here, it would represent 256. Another column would be 4096, and so on and so forth. Okay, so understanding that is really key to understanding how to convert these numbers, right? So if I draw my little table again, right, we've got instead of 8 columns, we've got 2 columns. We've got 2 columns, right? This column represents the 1s. This column represents the 16s. So if we're converting a hexadecimal number, and I tell you what, let's do that 3D. Let's do 3D. Okay, we have D 1s and we have 3 16s. Okay, so the way that it works is this. The first column you multiply by 16, yeah? And then you just add on the second column, because what you're effectively doing is multiplying it by 1, yeah? So if we've got 3 times 16, 3 times 16 is 48. Yeah, 3 times 16 is 48. And then D, we multiply that by 1. Well, anything multiplied by 1 is just itself, so we just need to convert that to a value, and that is 13. Okay, I've now got 48, and I add 13 onto that. 48 plus 13. Okay, so we end up with 48 plus 13. 8 plus 3 is 11. 4 plus 1 is 5. We end up with 61. Okay, so 3D in hexadecimal is equivalent to 61 in Daenery. Okay. So the thing to remember, first column, multiply by 16. First column, multiply by 16. Second column, just add it on. Yeah, the first column, multiply by 16. Second column, just add it on. Why the... I have no idea what you guys are chatting about down there. Denisa helped you. Denisa is good at helping. Do we lose marks if we convert it to binary then Daenery? Probably, right? Probably, because they will often say in the question, do not convert to binary first. You need to be able to do it directly like this. You need to be able to do it directly like this. Okay. I will say, if this method, if you completely forget how to do this, right? If you do convert it to binary and then write the answer down, you might get like half a mark. Denise's probably great at slapping as well, although I don't know. I refuse to believe that she could ever be violent. Anyway, so yeah, so just make a point of this. First column, you will never get more than 2 columns as well. It's always going to be a 2-digit hexadecimal number. So multiply the first digit by 16, multiply the second digit by 1, and then just add them together. Okay? So first one times 16, add on the second one, there's your answer. Yeah? And obviously, if the first digit is like if we were converting, I don't know, something like let's do A4. Yeah, A is 10, so we would do 10 times 16, which is obviously 160, and then don't forget to add on that 4. We get 164. Okay, does that make sense? Oh no. Oh no, there's xenophobia going on in the chat. Don't make me ban people. Right, so there's one final conversion that we need to be able to do, and that is Daenery to hexadecimal, which is probably the most infuriatingly annoying one of all of them, right? So Daenery to hexadecimal. Does anyone need me to go over any particular bits of this conversion before I delete it? Anyone got any questions on that? What's the question? Or are you just lying to me? I will get you, Scarlet, if that is your real name. I'm absent-mindedly rubbing Tiger Balm on me. Why did my dad leave me? I can't answer that question. I don't know enough about you or your dad to answer that question. I suspect, though, it might have been like asking too many silly questions in YouTube chats. Maybe, I don't know. Why did my dad? No, I'm not going down that route. I'm not going down that route. You're trying to distract me from my true purpose. Oh, I've got Tiger Balm in my eyes. Right. Anyway, let's delete this. Ow. Note to self: do not put Tiger Balm in eyes. It smells so good, though, man. Oh, it smells so good. Tiger Balm. Yeah. Right. So we're gonna do a. There's no such thing as too much Osu. There's no such thing. Let's go to a Daenery number. Let's take a Daenery number. Let's do, I don't know, 143. 143. Let's do 143. This is going to be good day, Smith. Thanks, Scarlett, for your enlightening conversation. We got 143, okay? What you have to do to convert this is you have to divide by 16. You have to divide by 16. No one likes dividing by 16. That's awful. What's 143 divided by 16? Especially on a paper where you don't have access to a calculator, right? How many 16s are there in 143? I don't know. You know what? I am just going to quickly use my calculator. I suck at division. I hate it. I hate it. I was absent from school the day they did long division, and it was just a day. So I never properly learnt how to do it, and I've never forgiven myself for that. So let's do 143 divided by 16. 143 divided by 16 is 8. There are 8 16s in 143, with some left over, obviously, right? So 143 divided by 16 equals 8. All right. Now, if we want to work out how much is left over, we do 8 times 16, and 8 times 16 is 128. Should have known that. Okay, and then what we can do is subtract 128 from 143. And I hope at home you guys are sat there going, are you serious? Is this what we've actually got to do? Because like I do have an easier way of working this out. But I'll go, I've started now, so I've got to go, I've got to carry it on to the end. 13 minus 8 is 5. That is now 3. 3 minus 2 is 1. And 1 minus 1 is 0, right? So 143 apparently is 143 minus 128. 143 is, yeah, is 16 remainder 15, right? 16 remainder, sorry about my handwriting, 15, okay? Sorry, it's not 16, it's 8. It's been a long day, all right? 8 remainder 16. So if we're converting this number to hexadecimal, this 8 is our first digit. This 15 is our second digit, so we would convert it. We'd end up with 8F, right? Now, that whole process, God, that's horrible, right? If only there was an easier way. Well, don't worry, friends. I'm going to show you the easier way, because there is an easier way. There's almost always an easier way. It's just sometimes the easy way takes a long time. So we're still going to start off with 143, right? But let you into a little secret. Dividing by 16 is the same as dividing by 2 4 times, right? That's just simple maths, okay? So if we want to be able to divide 143 by 16, and your 16 times tables are kind of rubbish, one way of doing it is just dividing by 2 4 times, okay? So if we divide by 2, we end up with 143 divided by 2 is, you know what, I'm going to get rid of that. 143 divided by 2 is 2's into 14 is 7, remainder nothing. 2's into 3 is 1. So it's 71 remainder 1. Yeah. If you've got an odd number and you divide by 2, the odd number is going to have a remainder 1, an even number is going to have a remainder 0. So that's dividing by 2 once. Let's divide by 2 again. 71 divided by 2. How many 2's are there in 7? There are 3 2's in 7. With 1 left over. How many 2's are there in 11? There are 5. So 35 remainder 1. Yeah. Divide by 2 again. 35 divided by 2 is 17 remainder 1. Yeah. And 17 divided by 2 is 8 remainder 1. Okay, cool. Look, we've got that first, we're back at that first digit. We've divided by 16. Because when you divide by 2 the first time, that's like saying we've just divided it by 2. If you divide by 2 again, the running total, if you like, is actually dividing it by 4. If you divide by 2 again, the running total is dividing it by 8. Yeah. And if you divide by 2 again, sorry, that's 2. If you divide by 2 again, you've divided by 16. Yeah, so that's how that bit works. So now we need to know what to do with these remainders that we've been keeping track of, and they can tell you what the second digit is. If you take those remainders as you've written them down there and you rotate them down like this, okay, so that one goes down here, that one goes down here, that one goes down here, and that one stays where it is, you end up with, I mean, this is probably a crap example because it's going to be the same order anyway, 1 1 1 1. You end up with this 1 1 1 1. That, if you convert that to Daenery as if it's a binary number, that will tell you the answer. So if we use our magic numbers, there's 8, there's 4, there's 2, there's 1, right? 8 plus 4 plus 2 plus 1 equals 15. Oh, look, it's the same thing that we had before. 15 equals F, right? So we end up with 8F. Yeah. So one way of doing the Daenery to hexadecimal conversion, if you can't divide by 16, I mean, they will usually give you some numbers that are fairly clean divisions, but if you can't do it, divide by 2 4 times. Note down the remainders, rotate the remainders, and convert to Daenery. All right, I'll give you another example with a different set of numbers that doesn't just come out as, like, 8 4 2 1, all the ones like that. So let's do this. Going to delete all of that stuff. Let's start off with another Daenery number. We will have, what number are we going to have? Let's come up with just a random number. Let's do I don't know, 76. Should we do 76? Yes, sir. Let's do 76, right? So same deal applies. First of all, divide by 2. 76 divided by 2 is 38. Is that right? 38 remainder 0. 38 remainder 0. Yeah. 38 divided by 2 is 19 remainder 0. 19 divided by 2 is 9 remainder 1. And 9 divided by 2 is 4 remainder 1. Okay, so we end up back in this situation. This is still our first digit, and then we take these numbers here and we rotate them round, so we end up with 1 1 0 0 because we've rotated them round this way. We then just do that conversion. 8 plus 4 plus nothing is 12. So 12 is our second digit. Okay, so 12 is C. So 76 when converted to hexadecimal is 4C. Okay. Does that make it a little less bothersome doing that conversion? Oh no, I've killed them all. I've killed them all. Do you guys exist? You still a thing? Oh no. Oh, well, there's no one there. It does say that there's, wow, 6 people watching. Whew. Average view duration 8 minutes. So good. Right. Anyway, hopefully that makes sense to all of you, and we can move on. If I just have a look at my, so we've done binary conversions. File size calculations is the next one. File size calculations. I think before we do file size calculations, though, it makes sense to go over storing images, sound, and text as binary, because being able to calculate the file sizes kind of requires you to understand how they are stored. So let's just go to this thing about character sets. Is that going to load? Probably not. There we go. So if I just turn off my amazing whiteboard here. ASCII is one of the character sets that you need to know. The standard ASCII has 128 different characters. Most of the time these days when we talk about ASCII, we mean extended ASCII, which has 256 characters. Look, there they are, right? This here is a character set. The things in red are the characters, yeah? And you'll notice that each of these characters has a unique value assigned to it. A unique value. In the computer system, it will actually be binary. In this little table that I've got here, it lists the Daenery, the hexadecimal, and the octal for some reason. Okay, but in the computer system, the computer will have them mapped as binary. You'll notice that the first 32 characters are not printable. So we have even fewer characters in the ASCII character set. Unicode uses more than a single bit, and so there's a lot more characters that we can represent. All right, but if you understand how character sets work, then you will also understand how images work. You will understand how sound work, because it's pretty much the same thing. Okay, so if we have a text file, text is made up of multiple different symbols, right? So each of the symbols is looked up in the table for the character set, and the equivalent binary number is written down. That binary data is stored. If we need to restore the text, we look up each binary value in the text file. We look it up according to the character set that's in use, and we just print out whatever character is associated with that unique binary value. Here's a reduced section of the ASCII character set, and you can see the binary codes here. Okay, so a lowercase letter A has the binary code 01100001. The only character that has that code is the letter A. It is unique to that letter. Capital A has the binary code 01000001, which is almost the same. You'll notice the lowercase letters on the left-hand side are almost exactly the same as the binary values for the uppercase letters on the right-hand side. The only difference is this third bit is on for all of the lowercase letters. Okay, neat little thing. Okay, so if we were to convert the word hashtag YOLO, you can see how long ago it was that I wrote this. All we do is look up the hash symbol, look up the Y, look up the O, look up the L, and so on. Let's not bother with the hash symbol. Let's just look up YOLO. So we go back here, and Y is 01011001. O is 01001111. L is 0100111100. So if we were to store the string YOLO, the binary would be 01011001, 01001111, 01001100, 01001111. Hopefully that makes sense to everyone. Okay, we're not going to do that worksheet, but we are now going to move on to images, which are pretty much the same thing, except instead of letters, instead of symbols, we have pixels, right? Each pixel can be a specific color. Each color has a unique binary value associated with it. Yeah, so on a very, very basic level, if we just have two different colors, yeah, in this example we've got the dark green and we've got the light green, yeah. Dark green is represented as 1 and light green is represented by 0 in this example. The first pixel is 1, the second pixel is 1, the third pixel is 0, the fourth pixel is 1, the fifth pixel is 1. On the next row, we've got 1 0 1 0 1. The next row, 1 0 1 0 1 1 0 0 0 1 1 0 1 0 1. We don't store it in blocks like this though. It's just a long stream of binary like that. Okay. There will be additional data about the height and width in pixels of the image. Okay. A more realistic version is not having just two colors, but having multiple colors. The number of bits per pixel determines how many different colors can be in the image. If you have 1 bit per pixel, you can have 2 colors. If you have 2 bits per pixel, you can have 4 colors. If you have 3 bits per pixel, you can have 8 colors. If you have 4 bits per pixel, you can have 16 colors. 5 bits per pixel, 32 colors. 6 bits, 64 colors. 7 bits, 128 colors. 8 bits per pixel, 256 colors, and so on and so forth. Adding a single bit per pixel will double the number of colors that those pixels can be. Okay, so the colors themselves are stored in this lookup table, very similar to like an Ascii character set or something like that. It's just a color table, and they have a unique binary value associated with them. Each pixel in the image, therefore, can be stored with a binary representation corresponding to the color that that pixel should be. In this example here, we have a red pixel. Red in the table is 0, 0. So this first pixel is going to be represented by 0, 0. We then have a white pixel. In our table, that is 1, 1. So the next pixel is going to be 1, 1, and so on and so forth. Blue is 0, 1. Yeah, you'll notice black is not actually used in this image, right? But it's still an option. If we wanted to include some black on this image, we could just color the pixel in and just change the bit value to 1, 0. Okay, so remember, the more bits per pixel you have, the more colors you can store, but obviously that's going to increase file size as well. So if we were going to go through and store this whole lot, we would have 0, 0, 0, 1, no, sorry, 0, 0, 1, 1, 0, 1, 0, 1, 1, 1, 0, 0, 0, 1, 0, 1, 1, 1, 0, 0, 1, 1, 0, 0, 1, 1, 0, 1, 1, 1, 0, 0, and so on and so forth. And as before, we wouldn't store it in a big block like this, we'd store it in a long stream of binary. Okay, generally speaking, looking at long streams of binary is enough to give most human beings a headache, or it's going to be difficult for you to distinguish between the different ones and zeros. So normally when we're looking at big pieces of data like this, it would be represented as hexadecimal. Okay, so each byte can be represented by 2 digits of hexadecimal, which makes it, first of all, a lot easier to read, and secondly, it makes it take up a lot less space on the page if we're looking at that. Okay, so remember, each pixel can be a single color. There is a list of colors which are assigned unique values, and then whatever color that pixel corresponds to, the bit pattern for that color is stored. Yeah, if we're restoring from binary data, all we do is check out how many bits per pixel it is, read that number of bits in, look it up in the color table, and draw that color pixel. That's literally all there is to it. So you can see images are basically just the same thing as text files. Instead of a character set, images have a color table. That's all it is. Okay. We're not going to do part 2 of the worksheet. We're not going to do hacking video games. I apologize for that. We are going to... Oh, no, did not mean to do that. I've just messed up my entire life. I meant to do that. Should we talk about digital audio? I'm going to skip past some of this stuff because you know what sound is and you know what sine waves are, and we're not watching those annoying videos. Okay. But one thing that you need to understand about digital audio is that it uses these things called samples. A sample in digital audio is roughly equivalent to a pixel in a digital image or a character in a text file, right? So when you record sound, you take regular measurements of the height of the wave, right? Each of those measurements is called a sample. And you take a whole bunch of those measurements so that you can reconstruct the wave later. The rate that we measure the height of the wave is called the sampling frequency, which is measured in hertz. So if you have a sampling frequency of, I don't know, 40 kilohertz, that means you are taking 40,000 samples per second. How does this apply to animal care? Who knows? That's left as an exercise for the reader. Here's an example. We've got a sound wave here. You can see that each sample is taken at a regular time interval. The first sample records this height. The second sample records this height. The third sample records this height. The more samples you take in a given time, the higher the quality of the sound. Therefore, increasing the sampling frequency increases the quality of the sound. Okay, we don't need to know about that. Not going to talk about that. Let's talk about bit depth though, right? Just like with images, each pixel can be a different color. With sound, you have different heights of the wave. Right, that's what we convert each of the samples to. So you can see here on this little diagram, I have partitioned the height data into these specific lines, and you'll notice as well when we measure the height of the wave, those samples have to snap on to one of these lines, right? This first one, we measure that. Oh, that's -4. That's fine. Okay, this next one is a 0. This next one is a 4. This next one, if you look at it, the actual wave is halfway between 6 and 7. But it's just a little way past halfway, so we end up saying that's 7, because we can't have a value in between 6 and 7. Okay? So each of these samples will be mapped to the row, if you like, which is closest to where the wave actually passes down. Yeah, but obviously computers aren't going to store things as like Daenery values which start at 0 and go to -8 or +7. They store them as binary data like this. Okay, so the lowest point in this example might be 0, 0, 0, 0, the next one 0, 0, 0, 1, and so on and so forth, all the way up to 1, 1, 1, 1. Okay, so once we've measured every point along that wave and we've snapped it onto one of these levels, we just write down the binary for the level that each sample is at. Okay, so this wave would be 0, 1, 0, 0, 1, 0, 0, 0, 1, 1, 0, 0, 1, 1, 1, 1, 1, 1, 1, 0, 1, 0, 1, 1, 1, 0, 0, 0, 0, 1, 1, 1, 1, 0, 0, 1, and so on and so forth, right? And just like with images and with text, you just have that long stream of binary, okay? So the things that affect the quality of a sound wave: the higher the sampling frequency, the higher the quality of the sound wave. And the more of these levels you have, the higher the quality of the sound wave, right? So if I have, I don't know, I've got 4 bits per sample here. I've got 16 different levels. If I had 5 bits per sample, I would have 32 different levels. So there would be a line in between each of these lines. You double the amount of levels that you have, and that allows you to more precisely map the wave, right? So higher sampling frequency increases the quality, and higher bit depth also increases the quality. Yeah, in the same way that for an image, more pixels increases the quality, and a higher bit depth per pixel will increase the number of colors. Yeah, in text files, more bits per character increase the number of different symbols you can display. I hope that makes sense to everyone, because I'm now going to spend about 10 minutes just going over calculating file size. I don't want any children, thanks. There's no need. If you don't want them, just recycle them or something like that. Okay. So should we go over calculating file size? We'll do it for text files, we'll do it for image files, we will do it for sound files as well. All right. So I just need to bring up my amazing whiteboard once again. Feel free to ask any questions while I'm sorting this out. I think Bill is in love with you. More fool him, I shall say. More fool him. Nobody loves me. Nobody should love me either. I am an unlovable man. Right, so let's say we have a file. We'll do it for a text file first of all, right? I should probably use the text tool to do this. Text. Let's say we are using Ascii, which is 8 bits per character. Okay, Ascii is 8 bits per character. Yeah. So let's say our text file has, I don't know, 1,500 characters in it. We've got 1,500 characters. Sorry about my handwriting. All we have to do, multiply the number of characters by the bits per character. That tells us how many total bits there are in that file, right? So I do 1,500 times 8. What's 1,500 times 8? What's 15 times 8? What's 5 times 8? 5 times 8 is 40. Oh God, I can't do maths. You know what? I'm not in the right frame of mind for this because I'm looking at the chat and people are talking about me being a tree surgeon. It was pretty cool, to be fair, but I did nearly cut my thumb off with a chainsaw once. So there's, you know, swings and roundabouts. Right, it's 12,000. 12,000. That's 120,000. Come on, Smith, wake up, for God's sake. 12,000. There's 12. It's not lined up. I don't care, right? 12,000. Now, that's 12,000 bits. Okay, so you multiply the total number of characters by the number of bits per character. That tells you how many bits there are. In order to work out how many bytes there are, you then have to divide by 8. Well, if you're doing ASCII, then that's pretty easy because you just multiply by 8. So we're back to 1,500 bytes. Okay, so our text file that contains 1,500 characters is 1,500 bytes. We probably wouldn't display it as bytes though. We would display it as 1.5 kilobytes. Right? Calculating the size of text files is trivial. Yeah, multiply the number of characters by the number of bits per character. If necessary, divide by 8 to work out how many bytes there are, and then obviously display it. Divide by 1,000 if you need to, or 1,000,000 if you need to display in megabytes. Okay, so that's text. I hope that makes sense to everyone. If it doesn't, now is the time to let me know because I'm about to move on to images. I'm sure I had a presentation about this, but who knows? Okay, so let's say we have an image which is let's actually use the right tool. Let's say it's I don't know, 150 pixels wide by 200 pixels tall. Okay, that's our image, and it is using Let's go with 4 bits per pixel. Okay, so we've got 150 pixels wide and we've got 200 pixels high, and we've got 4 bits per pixel. You need 180 or 180 wide. Okay, we'll do 180 wide. There you go. Hope that satisfies you. Okay. I don't know why I'm capitulating to you, but maybe if it fulfills whatever sick, twisted fantasy you have about the number 180. So first of all, we need to work out the total number of pixels, right? So we do 180 times 200 to work that out. Again, I'm just going to use a calculator because I'm a failure. 120, sorry, 120, what am I doing? 180 times 200. I should know this is 36,000, right? Because 18 times 2 is 36, and then you just add those things on there, right? So there's 36,000 pixels, right? 36,000 pixels. Once we know how many pixels there are, we just have to multiply that by the number of bits per pixel to find out how many total bits there are. Okay? Times 4 bits per pixel. Okay? So 36,000 times 4 is 144,000. 144,000 bits. That's the total number of bits in the image. The total number of bits in the image, right? We now need to work out how many bytes there are, right? How many bytes there are. So we have to divide by 8. We divide by 8. Okay, so 144,000 divided by 8. So once again, divide by 8 for bytes. And we end up with 18,000 bytes. Okay. Now we're not quite done yet. That's the total number of bytes that are used for the data itself, for the image data. But we also need to store the metadata. Am I home? Yeah, I am. Why? You're coming round, are you? So I'm storing the metadata. The metadata is all the information about the image itself. So it might be the width, the height, the program that was used to create it, etc., etc. It's a pretty nice house. You can just see my telescope there. One of my telescopes. I've got 2. My guitars are down there as well. But this isn't about my house. This is not MTV Cribs. So yeah, so we need to add on the metadata. As a general rule, we say the metadata is 10%, right? So I'm just going to draw a little arrow up here. Yeah. So we're adding on 10% for metadata. Okay. So 10% of 18,000 is 1,800. So we're just going to do 18,000 plus 1,800, and we end up with 0089. That's an 8. Sorry about my terrible thing. So we end up with 19,800 bytes. Okay, but oh, is that you, Harrison? Good to see you. We obviously need to convert that to a more sensible measurement, because we wouldn't say 19,800 bytes. We would divide by 1,000 and say 19.8 kilobytes. Remember, capital K, capital B. Okay? So, just in summary, multiply the width by the height. Multiply that total by the bits per pixel. divide that total by 8 to get the total number of bytes, add on 10% for the metadata, and then convert to a relevant size. Either divide by 1,000 or divide by 1,000,000. Just keep on dividing by 1,000 until you get to a reasonable number, but make sure you keep track of how many times. If you divide by 1,000 once, it's going to be kilobytes. If you divide by 1,000 twice, it's going to be megabytes, and so on and so forth. What on earth is going on there? It is a Celestron. It's a Celestron SLT 130. Hang on, I'll tell you what it is. I've had this ages. It's a Celestron Nexstar 130 SLT. It's got computer control. It's not as good as my it's not as the aperture is not as wide as my that one there. That's my big boy. That is a 250mm aperture, which is nice, but it's only a Dobsonian, so it's sometimes difficult to track stars with it. But there you go, right? So there was a little bit of a house tour. Anyway, does that make sense in terms of working out the file size of images? I'm telling you, man, Tiger Balm is the future. Get some Tiger Balm. Right, cool. So the final thing then is sound files. And the thing is, it's pretty much exactly the same. If you understand that samples are like pixels for sound, the actual calculations are pretty much the same thing. Oh, nice work. Nothing better than a job offer. That's cool. Yeah, you'll have to drop me an email and let me know how you're doing. I want deets. Fill me in on the deets. Right, so let's talk about sound files, right? Let's say we have a sound file which is, let's say it's 30 seconds. Right? And it has been sampled at a rate of 11 kilohertz. I can actually write this is a mouse, right? And it has a bit depth of, let's say, 16 bits per sample. Okay, 16 bits per sample. Okay, so first of all, we need to multiply the length of the sound by the sampling frequency. But you've got to be a little bit careful, because remember, if it's kilohertz, that means 11,000. Yeah. So in this example, we're going to do 30 times 11,000. All right. 30 times 11,000 is right. Guys, can you just be nice to each other, please? There's no need to not be nice. Always be nice. That's what I say. Always be nice. If the nicer you are, the nicer the things, the nice things will happen. Or something like that, right? That means there is a total of 330,000 samples. Right, a total of 330,000 samples. Well, we know that there's 16 bits per sample, so we just have to multiply 330,000 by 16. Yeah, 330,000 times 16. Okay, and 330,000 times 16 is 5,280,000. And that is the total number of bits in the total number of bits in the sound file. You see the similarities here, right? Instead of doing width times height and then times bits per pixel, you're doing length times frequency and then times bits per sample. But it's the same thing. So the next stage is then to divide by 8, right? To find out the total number of bytes. And that gives you, let's divide that by 8. 660,000. 660,000 bytes. Just like with images, we need to add on 10% for metadata, right? So plus 10% metadata. Okay, that means we're going to do 660,000 plus 66,000. Yeah, and we end up with 0, 0, 0, 6. That's a 12, and that's a 6 plus 1 is a 7. We end up with 726,000 bytes. But obviously we probably want to convert that to kilobytes, so we would divide by 1,000 and we'd end up with 726 kilobytes. Okay, how many marks would this question be? Probably about 4. Probably about 4. You'd get a mark for working out the total number of samples. You'd get a mark for working out the total number of bits. You'd get a mark for working out the total number of bytes, and then you'd get a mark for the final answer in a suitable format. Right. I think I might already watch some Astro Biscuit stuff. I'm not sure. Mad ting. Does that make sense to everyone? Tonight we have covered systems architecture. We've covered all of the elements of the CPU. We've looked at cache. We've looked at number of cores. We've looked at clock speed. We've done binary conversions, all of the different binary conversions that you need to know. We've done file size calculations. We've done how images are stored, how sounds are stored, how text is stored, and we've done working out what the file size would be for any of those files. I know it's been about 2 hours ish. I mean, obviously there was about 15 minutes at the start when I was setting stuff up, but I hope that you guys are feeling a bit more confident about that stuff, because that stuff is stuff that we have done a long time ago. Are you bringing orange juice and homemade chocolate banana cake before the exam? Not everyone gets the same level of love as you did, Gabe. Is that Gabe? I think it's Gabe, if I recall correctly. That is your that was your username. So I'm glad you've learned so much, Scarlett. Imagine how much more you could learn if you were there in my lesson from the start. You know, but you know, some people make bad choices in life, like deciding not to do computer science GCSE. Terrible choice. Still free to do computer science A level. You know, just throwing that out there. Just a thing. Cool. So now is the time for you guys. I took drama. Unlucky. I get enough drama with my year 8 students. Don't need any more than that. And when I was your age, I got enough drama from my annoying sister. So that's still the do a Michaela. I'm not commenting on any of my former students. Now then, now is the time for you guys to ask me any questions that you might have before we sign off and I disappear and you can no longer look at my face. I mean, you probably think that's a good thing. You don't want to look at my face anyway. But does anyone have any questions? Average view duration 11 minutes 44. Really? Like they tune in and they just switch off. Oh no, I don't want to pass. I want to fail. I'd sooner fail. That's the general view. Zoomers, man. The future is dead before it starts, isn't it? Prove me wrong, guys. Prove me wrong. Be excellent. Tell your friends to be excellent. No one's got any questions. No one's got any questions. Have you got married? No, I don't believe in the concept of marriage. It's just archaic patriarchal oppression. Mad. What's mad? Also, marriage is not really related to computer science. When I said any questions, I meant questions about computer science, not questions about me. I'm right. So I'm glad you guys were so focused on the stuff that I was telling you, rather than like what was going on in the chat there. Any genuine questions? What's your question, Bill? It better be a good one or I'll hunt you down in Minecraft. How long is the exam? Hour and a half. If I fail computer science, can I redo it? No. No others? No more questions? Can Denisa redo it? No, no one can redo it. There's no preferential treatment. I don't rate any of my students higher than others. Okay, no one gets any special treatment. It's just the way it goes. Yeah, that's right. Won't have to, because you're going to pass anyway. Going to absolutely smash it. Shut. Right. Okay. I think we've probably reached the end of our journey here. Thank you for turning up. The 6 of you who did, even though one of you is not not even on the course. Wait. What am I waiting for? I did not fail computer science. I have a degree in computer science. Although what I think you might be referring to is my GCSE. When I was at school, computer science was not a GCSE option, but there was an IT, or the one that I did was called IS, Information Systems, and it was so boring. It was so boring. We were learning like how to use spreadsheets and stuff, and I was already programming. I'd already been programming for years at that point, and everything was just so easy. I just could not be bothered. I also switched schools in year 10 because of an incident with a fist and a teacher, which is a story for another time. And so it was kind of up in the air. I was a bit of an idiot when I was a kid, but I got a C in my information systems GCSE. It was the lowest of all of my GCSE results. It was pretty awful. And and obviously it did not reflect my ability in computing. There was no A-level option computer science when I was your age. I did maths, further maths and physics. I went on to university to study computer science, and I got a computer science degree, and then I got some jobs which I thought would be my dream job, like working in the video games industry, and I realized that working in the video games industry was not good in any way. And what do you do when, like, you've had a dream your whole life and then you realize that that dream is nothing more than an absolute shattered nightmare? And so now I decided that, I mean, one of the reasons why I became a teacher was because a lot of the teachers that I had were really boring and kind of rubbish. This was a long time ago, obviously, and so I took inspiration from my old maths teacher, Mrs. Cheney. Was a fantastic teacher, and I thought if I could do a job just half as good as she could, and encourage others to be the same, then I will have made something good happen in the world. And I spent so long making bad things happen in the world that I needed something good to happen. So one of the reasons I became a teacher was to just help young people learn about computers, and learn in a way that was more than just, here's the stuff you need to know to pass an exam. As people on my course are well aware, I don't just teach the stuff which is on the spec. I teach you more than the stuff which is on the spec. I teach you stuff which is interesting, and then I show you how that can work towards, like, you know, the actual passing of the exam, because the exams themselves are basically just hoops that you need to jump through. I say this in every subject, not just in computer science, in every single subject. Your employers are less interested in what grade you get. They are more interested in what you can do, right? So my advice is, whatever career path you are interested in, if there's things like that you could do to build up a portfolio of sorts, don't waste time. Get doing it. If you want to be an artist, then you can did make Lord of the Rings Online. Yeah, that wasn't a bad thing. That was a good game. Yeah, if you want to be an artist, get drawing, make pictures. If you want to be a programmer, get coding, write some programs. You know, your potential employers are going to be more interested in seeing what you can do than seeing what letter or number appears on a piece of paper next to your name. So I will say this to you: although the grades that you get at GCSE do not define you, they do open doors for you. The better grades you get, the easier things are in the next stage, if that makes sense. Decent GCSE grades make it easier for you to access A-levels. Decent A-level grades make it easier for you to access university. They do not define you as a person, and you shouldn't stress out about them as if it's like the end of the world if you fail. But at the same time, you should try to do your best, the absolute best that you can do, simply because they're going to make your life that little bit easier at a time when your life is sort of like being a teenager is hard, man. I did that once. I would never do it again. You know, no thanks. So there we go. There's a little bit of a motivational talk for you as well, which I needed to rein in a little bit. Otherwise, I was going to end up oversharing things. So can we see a house tour? Unfortunately not, because my webcam is plugged into my computer and I can't really move it around. And also the house is an absolute mess right now. I've had zero time to take care of my house recently because I've been marking year 13 coursework. I have been out and about doing other things, and I haven't really been able to tidy up. I can give you a little I can show you on the wall there. you will notice that sword, that is a scissor blade from the anime Kill la Kill, which is one of my favorite animes. That is a metal blade which has been it's like anodized aluminium or something. Some of my former students had that made for me as a leaving present, so I was super chuffed with that. What else we got here? There's that. My mum made that. So yay. There's Motoko Kusanagi. I bought that statue as a reward for myself for making it through university without dying. This picture of Alan Turing was drawn for me by a very good friend of mine. So I framed it, put it on the wall. That there is the album artwork for my first album. There's a plant in the corner there. There's my telescopes there. There's a dinosaur picture on the wall. The painting on the wall behind me, which I'm trying to see if you can see, that painting there in the background is Nighthawks by Edward Hopper, which is one of my favourite paintings of all time. There is a little thing on the you can't really see it, but there's underneath my shelves, the night sky on the day I was born. That was given to me by another close friend. And then there's a over there. There is the Litany Against Fear from Dune, and messy stairs. There's some masks on the wall there, cycling helmet, various other bits and bobs. Okay, I don't have a portrait of Ada Lovelace, unfortunately. The only woman I ever loved. She died 100 years before I was born. So yeah, I would take you upstairs, but you gotta earn that. There's not I mean it's really not much to see. The downstairs of my house is just all one big room. It's like all open plan, and then upstairs is the bedroom and the studio where I do my painting. There we go. Like I said, it's a mess. If you know anyone that can clean my house up for me, then let me know. Anyway, that's enough of an insight into my life. I hope this has been enlightening for you, and I hope that you continue to be happy in whatever you end up doing for the rest of the evening. How does that sound? Oh, I've killed them. I've killed them with the sadness of my lonely, solitary existence. I'm depressed. Well, if there was a way I could make you happy, I'd do it, but there probably isn't. So if you think of anything, I guess let me know. Right, I'm going to bid you all farewell. Thank you very much for watching. Thank you for being good students and for being nice to each other. Buy me food. I refuse to feed your addiction to food or something. I don't know. Anyway, peace out.